Good morning, students. Today we are having our third lesson on the same chapter, electromagnetic induction and alternating current. In the previous chapter, we saw the laws of electromagnetic induction put forward by Michael Faraday. We saw two laws. The first law told us how electromagnetic induction takes place, or whenever there is change in magnetic flux linked with a coil, EMF is induced and a current is induced in the coil. And this current and EMF will exist only as long as the magnetic flux changes. If there is no change, there will be no induced EMF and no induced current. That is what we saw in the previous class. We also saw that according to Faraday's second law, the magnitude of the EMF produced is directly proportional to the rate of change of magnetic flux. And we saw the equation EMF is proportional to d phi by dt. D phi means change in flux, the final flux minus initial flux, and dt is the time interval. So Faraday's first and second law gives us what happens during electromagnetic induction, when the EMF will be induced, and what will be the magnitude of the EMF. Now, the third law of electromagnetic induction, which is Lenz's law, will tell us in what direction this EMF is induced. So today we are going to see Lenz's law that tells us in what direction the EMF is induced during electromagnetic induction. I hope you remember we discussed in the beginning of this chapter that there were three scientists who did the experiments almost at the similar time, but it was Faraday who first published it. The other two scientists were Henry and Lenz. So we will see the Lenz's law today. Is that clear to you?
Yes, teacher.
Okay, so let us see what is Lenz's law. Lenz's law, which is always called the third law of electromagnetic induction. And according to the law, the direction of the induced EMF and induced current is such that it opposes the change in the magnetic flux that produced it. We saw that there will be an induced EMF or induced current only if there is a change in magnetic flux. Now, Lenz's law states that the direction of this induced EMF and current is such that it opposes the change in magnetic flux. Let us see how it is done. In the previous class, we learned the equation for EMF. EMF is equal to d phi by dt. But Lenz's law adds a negative sign to it. Negative means it opposes the change in magnetic flux. It's in a direction that opposes d phi. D phi means change in
Teacher,
magnetic flux. Yes?
there was a negative in the second law also, right?
In the second law, it is given as given in your textbook that the negative of the rate of change. But usually the direction is given by the Lenz's law, not Faraday's law.
Okay.
Faraday initially only told about the magnitude of EMF, and the formula that directly comes from Faraday's law is that EMF is d phi by dt. But it was Lenz who introduced this negative sign to that equation. But for a clarity of concept, there in the law itself, it is mentioned negative of rate of change. Okay, but that idea of negative was brought actually by Lenz. So he is the one who tried to find in which direction this EMF will be induced. According to Faraday's law, as we have already seen in the previous lesson, whenever there is change in magnetic flux, EMF is induced, and as a result, there will be induced current. But according to Lenz's law, the direction of the induced current will be such that it opposes the change in magnetic flux. how will it oppose the change in magnetic flux? Let us see how. Here, consider a bar magnet which is moving towards this coil of wire which is connected to a galvanometer. Now, when you push the bar magnet into the coil of wire, what happens? It's the north pole going into it. So, how can this coil of wire oppose this motion? How can this coil of wire oppose this motion? The coil of wire want to push the bar magnet back.
So it
How?
needs an again north pole, right?
Yeah, so it needs a north pole here. It needs a north pole here so that it will oppose the bar magnet coming to it. So north pole, if it comes here, it will oppose or repel this north pole. So it will produce a current in such a way that there is a north pole there. So how the current will flow? The current will flow in this direction. If my thumb represents the direction in which the magnetic field is there, that is from north to south. If you want north pole here, what happens? The current should flow in this direction. That is anti-clockwise direction. So if the current flows in an anti-clockwise direction, here you will get north pole and here you will get south pole, because current flowing through a coil will produce a magnetic field, right? So if it is going in the anti-clockwise direction, what happens? Here a north pole and here a south pole is produced by the coil. So that north pole will repel this coming bar magnet. So it will try to oppose the magnetic flux change that produces the current itself.
Teacher, can you repeat that part? Fleming's right hand rule.
Yeah, here a bar magnet is coming towards the coil, right? So the coil want to repel the bar magnet back. How can I repel? How can it repel the bar magnet back? Only if there is a north pole here. How can it produce a north pole here? Only if a current passes in the coil in the anti-clockwise direction. So if the current flows in the anti-clockwise direction, you take your right hand and curl your fingers so that in this coil, the current flows in the anti-clockwise direction. So how the thumb will be? The thumb will point from north to south. So if your thumb points like this side will be north pole, this side will be south, because the magnetic field is always from north to south, right? So if you hold in the anti-clockwise direction, your fingers curl, then the thumb will point in such a way that here you have a north pole and here you have a south pole. Is that clear?
Yes, okay.
Okay. So here I have shown a setup. Consider the setup which has a coil, a magnet and a galvanometer as shown here. If the north pole of the
Teacher,
magnet, yes.
can you explain again the Lenz law?
Okay.
Lenz's law, please.
Lenz's law states that the direction of the EMF produced inside the coil, you know that a EMF is produced or induced inside a coil if the magnetic flux near that coil changes. Now, this coil does not want the magnetic flux near it to be changed. You don't want to change the magnetic flux. So what it will do? It will produce its own EMF or current so that it can oppose the change in the magnetic flux. So this is Lenz's law. Lenz's law states that the direction of the induced EMF and induced current is such that it opposes the change in magnetic flux that produced it.
Teacher, this
Yes,
opposing is the nature of, it's the nature.
it's a nature. It's the nature of the coil of wire. We know that we can produce like a bar magnet by flowing current through a coil of wire, right? We can produce bar magnet just by a coil of wire carrying current is similar to a bar magnet. We know that. So if there is a coil of wire without any current, and if you are placing a bar magnet near to it, or if you are pushing a bar magnet near to it, what happens? You don't want the bar magnet to come near it. So what it will do? It will produce a current in itself, so that that itself can act as a small bar magnet that will repel that bar magnet. So making the bar magnet go away from it. You just want to oppose the change in magnetic flux. That is the nature of that coil of wire. And because of that nature, the current is induced in that. Is it clear?
Yes, teacher.
Okay. So the equation which we learned in the last class, EMF is equal to d phi by dt, and to that equation a negative sign is given by the Lenz's law, because it will be, the EMF will be opposite to the direction of change in EMF. So minus d phi by dt. So this is the final equation that is obtained from all three laws of electromagnetic induction, including Faraday's laws and also Lenz's law. So here in the
Sir,
setup, yes.
sir, can you show that same figure when the south side is facing the coil?
Yeah, I haven't saved such a figure, but okay, it will come. It will come. Let's see. So this is
I
the
mean, just tell
case.
that.
Hmm?
You can say with your, I mean, you can say that how it will be.
Yeah,
If
I'm
you,
going to say that. I'm going to. If the
okay.
north pole of the magnet is brought near to the coil, there will be deflection in the galvanometer because of the induced current. And the direction of the induced current will be such that you oppose the motion of the magnet towards the coil. So the induced current will move the want to move the magnet away from the coil. So as the north pole is brought near the coil, the induced current will be in such a direction that the phase of the coil will have north polarity, which means here there should be north pole. For that, the current should flow in the anti-clockwise direction. Okay, so the current will flow in the anti-clockwise direction when we bring a north pole towards it. Now, as you asked, if the south pole of the magnet was near to the coil, can you guess what will be the direction of the current flow? We need a,
Clockwise.
yeah, it will be clockwise, that's all. So we saw that if we change the polarity of the magnet, the current flows in the opposite direction,
Sir,
right?
how will be the magnetic lines?
Then the magnetic lines will be directed in this way. Here it is directed out. From north, it will be directed out. If this was south, south and north, then what happens? From the south pole, it will be directed towards. I have a whiteboard, but I don't
Yeah.
have a marker. That's why I cannot draw and show it to you. Okay. So let me check whether I have a marker. Oh, I'm sorry, I don't have a marker with me. Okay, I'll try to get a marker and show it. Or I think in the next slide it is there. So if you have a south pole here, these arrow mark will be towards the south because magnetic field lines are towards the south, and this current will be flowing in the clockwise direction because here there should be a south pole to repel. Okay. Another thing, suppose the north pole is here, south pole is here. Instead of bringing near to the coil, I'm taking it away from the coil. Then can you guess in what direction the current will be? I'm not bringing the magnet near to the coil. The magnet is already near to the coil. I am taking it out of the coil. You know, even if I take it out, current is produced, right? So can you guess what will be the direction of the current produced if I'm taking it out? If I'm bringing it
Same
in,
only, right?
tell me, I didn't hear you.
I guess same, teacher.
If you are bringing the bar magnet into the coil, the coil produces current in the anti-clockwise direction. We saw that. Now, if I am taking the bar magnet away from the coil, it will again create current in the anti-clockwise.
See,
No,
teacher.
teacher. There will be no current, right?
If I am
Because the
It will
taking
be
magnetic
current.
away, if I
will
am
be current.
taking away, then also the
There will be
flux is
deflection,
changing.
I think.
Teacher. Even if you're taking it, I mean, away from it, still it's opposite, right?
Yeah, it opposes. So what will be the direction of the current?
Same only because it still opposes.
It opposes, but now the bar magnet is moving away from it. So it want the bar magnet
Okay,
to
then it
come
will
towards
change.
it.
Oh yeah, then it will change. Yeah.
See, here the bar magnet is going into the coil of wire. So the coil want to repel the bar magnet. It don't want the bar magnet to come near it. Suppose the bar magnet which was near to the coil is taken away. The coil don't want the flux to change. It don't want the bar magnet to go away. So what will it do? It will try to attract it, right?
Huh?
Yeah.
But
It don't want the
I mean,
change in flux, my dear.
okay. Yeah, I got it. When it's changing
Initially,
again, so
suppose the
it's why.
coil is staying at peace, there is no flux, zero magnetic flux. Now, when you bring the bar magnet, the flux changes. Suppose it changes to 5 Tesla. So, when you bring it, the flux changes from 0 to 5 Tesla. The coil doesn't want it. So, the coil try to oppose the bar magnet from coming near it. So, it will try to push it away. It will try to repel it. So it will try to produce the same polarity, north pole near it, and the current will flow in the anti-clockwise direction. Now the magnet is already there. Okay, there is a 5 uh, Tesla magnetic field there. Suppose it's of 1 meter square. So 5 Weber magnetic flux is there. Now I'm taking away the bar magnet suddenly. So what happens? The coil already have 5 Weber magnetic flux. I'm taking away the bar magnet, which means I'm taking it to 0. I am changing the magnetic flux. So a current will be induced. The coil don't want to change the magnetic flux. Okay? So what it will try to do? It will try to attract the bar magnet. It don't want the bar magnet to go away from it. Okay, so which pole? If it want to attract this bar magnet, which pole should come here?
South, obviously.
South, obviously. So what should be the direction of current? What should
Clockwise.
be? Clockwise. That is it. So if you are moving the bar magnet into the coil and the current is flowing anti-clockwise, if you are taking it away, the current will flow in the opposite direction, that is clockwise. Is that clear to you now?
Yes.
Whatever way the coil doesn't want the magnetic flux near it to change.
So it
Is
can
it?
attract sometime, then repel sometime.
Yeah, it doesn't like change, that's all.
Yes, yeah, that's the main thing. Yeah, but
Doesn't like change. So it opposes the change in magnetic flux. This change can be increase in flux or decrease in flux. Whatever it is, it don't like to change the magnetic flux near it. Okay, so let us see why this Lenz's law occurs, or why do we need this Lenz's law? Okay, have you learned conservation of energy? Do you remember
yes,
what is conservation of energy? What is the law of conservation of energy?
the momentum, something. Oh, sorry, conservation of energy. No, no.
Not asking law of conservation
Total
of
energy
energy.
will be equal, right?
Total energy will be conserved.
Conserved.
Okay. Can any one of you tell me, Hasina, can you tell me the law of conservation of energy? South, can you tell me law of conservation of energy?
Energy can neither be created, neither be destroyed.
nor be destroyed, then
Yes.
it can
It
be
can be transformed from
One form
one
one
form to
form
another form.
to
to
another form.
another form.
That is law of
Yes.
conservation of energy. See, energy can be neither created nor destroyed, neither created. Does it sound like opposing the law of electromagnetic induction put forward by Michael Faraday? Michael Faraday told that EMF, what is meant by EMF? The energy given to each coulomb of charge to move through the coil. It is produced, which means energy is created. From where? That is the question. We know that law of conservation of energy states that energy can neither be created nor destroyed. But electromagnetic induction says that energy is created, electrical energy is created in the coil of wire, right? Can it be from nowhere? No, there should be
No,
some
teacher,
reason.
there is no energy created because
Yeah,
the coil is
Induced,
connected with
right?
the battery, right? Yeah, the
okay.
No, no, not
No,
that
energy
coil,
is
no,
Ben.
into
Irfan,
the
ওইটা না।
coil, the coil
Thale.
was not connected to battery. It was connected
খালি
only
কয়েলটা
to the
যেটা
galvanometer.
গ্যালভানের সাথে ছিল।
Oh, okay, okay, that one, that one.
Then
Yeah,
how?
there was a
How?
force, right? There was a force, the magnetic force.
Ah, the magnetic
Yeah,
energy gets converted to the
converted
electrical energy in a
to
nearby
energy.
coil. You guessed right. That is
Yes.
what is happening. So, what is happening when the magnetic flux is changing? So, if they are opposing the change, we have, in order to bring the magnet near to it, we have to push with more force, right?
Yes, teacher.
Okay. South, suppose you have a table at home and you want to move the table towards the right, and you are moving it to the right, but your sister want to move it towards the left, suppose. So if your sister moves it towards the left, that is opposing that, then South have to apply more force in order to move towards the right, right?
Yes, teacher.
Yeah. So in order to move a bar magnet into the coil, we have to apply some force. And where this force will give the mechanical energy for the bar magnet to move into the coil, right? So we are putting some mechanical energy into that effort. Now, if the coil is opposing this motion, we have to put more mechanical energy into that process. Is that clear? So this more mechanical energy gets converted to more and more of electrical energy. So what is happening? Lenz's law supports the conservation of energy. When we hear only the Faraday's law, we feel that how energy, electrical energy, that is EMF, that is current in a circuit, how it can be created from nowhere. It's not possible. It is opposing the conservation of energy. Then Lenz's law states that when the magnet is moving, current is getting induced, and when the magnet is not moving, there is no induced current in the coil. So there is a mechanical energy involved with the movement of the magnet. In order to move the magnet, we have to give some mechanical energy. And this mechanical energy is converted to electrical energy, which is the induced current. So now can you tell what type of energy transformation takes place during electromagnetic induction? From what form of energy to what form of energy?
Mechanical to electrical.
Yeah. So during electromagnetic induction, mechanical energy gets converted to electrical energy. Is that clear? And that
Yes,
idea
teacher.
is proposed by Lenz's law. So Lenz's law supports the conservation of energy. And Lenz's law supports where one form of energy is getting transformed to another form. Here, mechanical energy is getting transformed to electrical energy. So here, as you said, you asked me what happens if South Pole is coming to the coil, right? So if South Pole is coming towards the coil want to develop a South Pole of its own. So it will make current flow in the clockwise direction. So a South Pole will be developed here and it will repel the magnet. Okay. Now, if you are moving the bar magnet away, now you don't want it, the flux to change. So the coil will develop current, induce current in such a way that it will attract the bar magnet towards it. You don't want the bar magnet to go away. So it will develop a north pole near that, which means the current will flow in the anti-clockwise direction. Is that clear to you? The concept of Lenz's law?
Yes,
Yes,
teacher.
clear.
Yeah. So from all this, from Faraday's law and Lenz's law, we can finalize that the EMF, the amount of EMF depends upon the strength of the magnetic field because phi is equal to AB cos theta. So it depends upon the strength of the magnetic field, that is B. It depends upon the number of turns or loops in the coil because EMF E is equal to minus n d phi by dt if there are n number of turns. So if you use more turns, you can produce more current. It depends upon the speed of the coil or the magnet. See, speed is more means time is less. You know the time interval dt is in the denominator, right? EMF is equal to minus n d phi by dt. Time interval is in the denominator. If it is moving with higher speed, time will be less. So EMF will be more. So if faster the coil moves, or the magnet moves, more current is produced. And the direction depends upon whether the magnet is approaching or moving away. Also, whether the north pole is coming first or the south pole is coming first. Is it clear?
Yes, teacher. Teacher, can you turn off the recording? Wanted to discuss something.
Okay, okay.